Hunter Pence stands on a platform 15 meters higher and throws a baseball at an angle of 37 degrees above the horizontal. You notice that it reaches the top of its trajectory in 2.4 seconds. So the first part of the question asks, with what you're given here, can you figure out the initial velocity in the y direction and the launch speed? So you know that at the height of its trajectory, Vy equals 0. So you can use the equation Vy equals V naught minus GT. So 0 equals the initial velocity y minus the speed of gravity times time, which is 9.8 meters per second squared times 2.4 seconds. So then you get 23.52 meters per second equals the initial velocity in the y direction. Then to find out the total speed, you know that because the angle is 37, you know sine 37 v naught will equal the y velocity, which
v naught is the
v naught is the total initial velocity, and then v naught y is the initial velocity in the y direction.
On the y, okay, the y, the vertical.
Yeah. So you know that there's this equation we have, sine of the angle times the total velocity gives you the velocity in the y direction.
Right,
so we know the velocity in the y direction, so we know sine 37 v naught equals 23.52, and then you can just solve for v naught, and we get 39.2 meters per second. Part B asks how high does it go above its release point. So now we're solving for y. So we have y equals y naught plus v naught y t minus 1/2 a t squared, and a is gravity, which is negative 9.8 meters per second squared. So because it's half of that, it's negative. Because when you take the derivative of this, you want to get gravity. So when you're solving for velocity, is the derivative of position. So when you take the derivative of this equation, the 2 will come down here and be multiplied by the g over 2 to give you gravity. Yeah, so y initial is 15 meters, and the initial speed in the y direction we already solved for is 23.52 meters per second. Time is 2.4 seconds, and half of gravity, as I said, is negative 4.9 meters per second squared times t squared, which is 2.4 squared. So when you solve for that, you get 15 meters plus 56.4 meters minus 1.96 meters, which is 69.4 meters. So the maximum height is 69.4 meters. See, part C asks the time at which it lands. So for this one,
you basically just have to wait. Let me see if you basically just have to it has 0 velocity at the top, and you just calculate gravity times time, sort of.
Yeah. Well, you use the position is going to be 0, so you use the position equation. Y equals y naught plus v naught y t minus g over 2t squared. So y naught, it says he starts from a platform 15 meters high, so y naught is 15 plus v naught y t is 23.52
then you would add, that's the height?
Times time, which is what we're solving for. No, that's the y velocity, is 23.52 meters per second, and then time is what we're solving for, and then minus 4.9 t squared. So you can rewrite that equation as negative 4.9 t squared plus 23.52 t plus 15, and you get a quadratic, which you have to solve for using the quadratic formula, so which is negative b plus or minus b squared minus 4ac all divided by 2a. So b is 23.52, so you get negative 23.52 plus or minus negative 23.52 squared is 553 plus negative 4 times negative 4.9 times 15 is 294, and it's all over negative 4.9 times 2, which is negative 9.8. And so when you solve this, you get 5.36 for t, which you can round to 5.4 which is one of the answer choices.
I see.
So the total horizontal distance it travels, measured from the point on the ground directly below the release point to the point where the ball hits the ground. For this, you use the x direction position equation. So you have x equals x naught plus v naught xt plus 1/2 ax t squared. And this last term's going to go away because there's no acceleration in the x direction. So you have x naught is 0 because that's the starting point. So x equals 0 plus, you can solve for the x direction velocity in a similar way to how we solve for the y direction velocity. It's cosine of the angle times the total velocity instead of sine of the angle. So you have 0 plus cosine 39.2 meters per second times, we solved for the total time already, which is 5.4 seconds. And then you get 169 meters.
Sounds about right.
And so this is a picture. There's not really, maybe I'll hold it up.
You got, okay. It's hard to
Yeah, you
let's
can't
get up
really see
here
it.
backwards in the computer
Okay.
though.
Anyway, I'm just supposed to show you the whole problem. One of the parts of the problem asks for a picture, so that's what I was doing.
You realize it's still on recorded, right?
Yeah, I know. So now there's a couple extra credit points, which I think I should explain to you just because I can probably do it pretty fast. So, what's the speed of the ball when it hits the ground? Vy equals v naught y minus gt. This is just solving for the y direction velocity because we'll do the x direction separately and then we'll use the Pythagorean theorem to combine them. So, Vy equals v naught y, which is 23.52 meters per second, minus gravity times time, which is 9.8 meters per second squared times 5.4 seconds. So we get 23.5 meters per second minus 172.5 meters per second equals negative 149 meters per second. It's negative because it's in the downward direction, and that's Vy. And then Vx equals v naught x, because there's no acceleration in the x direction. And it's 31.3 meters per second, which we got by doing cosine of 37 times 39.2. And then, as I said, we use the Pythagorean theorem.
But there is acceleration in the x direction, just not involving it for that problem.
Yeah, there's air resistance, but we're supposed to ignore that just to make it simpler.
That wasn't what I was talking. I was talking about the fact that you're just calculating it the speed towards the ground, you're not calculating it based on the speed out in that one.
Well, for this one, we're solving for this for both of them. It's the total velocity vector for the final velocity.
Okay, that's it.
Okay, so it's 149 squared plus 31.3 squared, and the square root of that, which you get 152 meters per second, and that's the final velocity. So the ball hits the ground with a velocity of 152 meters per second. So let's see, G. What is the angle of the ball's velocity vector when it hits the ground relative to the horizontal? So for this, you're solving for this angle theta. Maybe I should hold it up again.
The theta is the right. It's hard to do this. Moving it backwards here-ish. No.
Theta, let me see.
Sorry.
It's right there.
Yeah, but I was right there.
Okay, so we can substitute in the values because we already solved for the velocity vectors for horizontal, vertical, and total. So we just add those on to the triangle. So the hypotenuse is going to be 152, which is the total velocity vector. The vertical velocity is going to be 149 because that's the y velocity. The horizontal velocity is 31.3 because that's the x velocity. And then you're trying to solve for the angle theta. So you know theta will equal, tan of theta is going to be 149 over 31.3. So then you know theta is going to be the inverse tan of 149 over 31.3. And we get theta equals 78 degrees. So the angle of the ball's velocity vector when it hits the ground is 78 degrees. It has a vertical component of 149 meters per second downward, and the horizontal component of 31.3 meters per second. So that's it. Can you
Sounds about right. Oh, there's a part H as well, though.
That's the extra. That's what I'm doing right now. That's explaining it to you.
Okay, so yeah, if we try to do that, that'd be infinitely recursive. Alright.
Okay, you can